Now we're going to talk about the difference between heat and temperature. Heat is energy. Temperature is a measure of the average kinetic energy that we can do with a thermometer. And while they're closely related, heat is thermal energy that crosses a boundary. And I want you to think about this as temperature and quantity. So for instance, if I had this little tiny cup and it was filled with boiling water and I poured it into a baby pool, it really wouldn't change the baby pool's temperature at all because it doesn't contain a lot of heat energy, even though my water might be boiling, which would give it a really high temperature. Now, if I had 5-gallon buckets of warm water that wasn't even boiling, but it was pretty warm, that would warm up the baby pool a lot. Even though the temperature would be lower than my boiling water, I would have more of that warm water. So those two 5-gallon buckets contain a lot more heat energy than this little cup of boiling water might. And we saw a video that was pretty good. I really like that explanation, but that's really the difference. So for our class, we're going to think about it as temperature and quantity. Now, something interesting happened when we decided to come up with our thermometers. We had one guy who put all the hash marks or the increments on the thermometer and then measured boiling and freezing, and that was our Fahrenheit scale. So our freezing came out at 32 and our boiling came out at 212 Fahrenheit. Now the guy who came up with the Celsius scale did it different. He figured out where freezing and boiling came up on the thermometer, and he labeled freezing 0 and he labeled boiling 100, and that's how we came up with that. Now both these scales can go into the negative numbers, and since this is the measure of the average kinetic energy and we can't go into negative energy, we had to come up with a third temperature scale, which is Kelvin. Kelvin is directly proportional to kinetic energy. That means right here at 0. That is the lowest temperature we can possibly go to. That's 0 Kelvin. That's called absolute zero. And that's where all our motion stops. And then we go into another state of matter, which is called a Bose-Einstein condensate. And we're almost there. We get very close to that right now. And so our conversion between Kelvin and Celsius is we take our Celsius degrees and we add 273, and that's going to get us our Kelvin scale. Okay, so we can write Kelvin or just a big capital K. The next thing we want to talk about is the difference between kinetic energy and potential energy. Kinetic energy is the energy of motion, and potential energy has a lot of definitions. For this unit, I want you to think about potential energy as the distance between molecules. So let's think about it as the distance. For instance, I have this pink eraser right here, flat on the table. It's got no potential energy. If I hold it up a little bit, it has some potential energy, because if I release it, it'll turn into kinetic energy and it'll fall. And the higher it is, the bigger the distance, the more potential energy that I will have. So for chemistry right now in this unit, I want you to think about it as the distance between the molecules, okay? Which leads us to our phase change graph. So when we think about phase change, for right now, I want you to think about this as water. And the first thing you need to know is where phase change happens, temperature doesn't change. So here's a flat area, and this area that's flat is our phase change. Okay, and here's where we're freezing and melting. So if this was water, and you need to know this is going to be 0 degrees Celsius. We are not going to work in Fahrenheit. Okay, and here I am boiling or I'm condensing. So these are our next phase changes. These are our flat areas. And this, our boiling temperature, is 100 degrees Celsius. Okay. So when I start down here, which is below 0, I have the solid. And I'm going to add heat energy to this, and my temperature goes up, which means the motion of the solid increases. So it's going to vibrate faster and faster. So on the sloping part, we have an increase in kinetic energy, and this is in all our sloping areas, okay? And so basically we're increasing the motion. That's what the heat does. And then once this solid hits to a phase change, it is a solid now, and it's going to go through this phase change, and it's going to turn into a liquid. So during this phase change, it starts as a solid and it goes into a liquid. So I have both phases here. This is all solid, then I have solid and a liquid. So again, once it turns into a liquid, I am going to increase the temperature of the motion, and these liquid molecules are going to start moving faster until they have enough energy to break apart and change phases, and this flat part is where the phase change happens. This heat increases the motion until I hit this flat part. So here I have this increase in motion, increasing kinetic energy. But here, the energy is going into taking these solid molecules and kind of giving them a little more space so they can move more freely. So my space between the molecules are changing. So during a phase change, my potential energy is increasing and my kinetic energy is the same. Okay, here there's no temperature change. So no, when a flat area comes, this is where a phase change happens, and this tells us sometimes what our substance is, because I know this right here is going to change phases at 0 and 100, so it's probably water. Okay, so when we draw these phase changes, I'm going to give you a few tips. The first thing we're going to do is label our temperature. Then we're going to label where our phase change happens. So for us, our phase change temperatures are 0 and 100 if we're talking about water. Then we're going to draw a flat line where these phase changes occur, and we're going to stagger them, and then we're going to connect it and make this phase change graph. So let's give that a shot. And what we have here is we're going from -5, so we're going to label those temperatures, to 110 degrees. Our next job is to label where our phase change happens, and this is water. So we're going to have a phase change at 0 degrees, right about here, and we're going to have a phase change at 100 degrees. Now I do need to warm up, but as soon as I hit 0 degrees, I'm going to have a phase change. So my temperature is not going to change at 0, but I'm going to warm up, and then at 100, we're going to have another phase change for water. So my solid increases temperature, and then it changes from a solid to a liquid. So I have both phases. And once it turns completely into a liquid, the temperature will start rising, and those molecules move faster and faster until they can change from a liquid to a gas. So I have both phases there, and then once it's completely into a gas, my temperature will start increasing and my molecules will move faster. So on the sloping portion of the graph, our molecules move faster. And on the level portion, we have our phase changes. And it's level because there's no temperature change. That's very important to remember. Okay, kinetic energy, our molecules moving faster, is happening on the sloping portions. Slope, slope. And our potential energy is increasing when our molecules are overcoming those intermolecular forces and getting more space between them. And that is on our flat portions, and that's where our phase change happens. All right, so give it a try.